No, I guess I envision it as more informative, like, so I did that speaking one, I was supposed to talk a little bit about how it's set up, and then you mentioned the deadlines.
Oh, very interesting.
And not just like
nothing
more
about your
not
project.
about
Yeah, and other opportunities that we have, and we're there to meet people and to talk to other people.
Yeah, that's cool.
It's more about like what it's like to go,
Yeah.
not specifically what we talked about.
Okay, let's get started. It's fine. I was just looking for a good place to catch you off.
Just tell us the shit.
Okay, so welcome back. Just a reminder, day number 1 quiz is due on Friday by 5 p.m. And we will continue in chapter 1 today. Are there any questions? Yes.
With the listserv, because I noticed a bunch of us, including myself, ended up sending 2 messages because it didn't show up right away. Is that because it's moderated and so we don't see it right away?
It's
or
not
is
moderated.
Okay.
In my other class, it's the same problem. I don't know why there was a delay.
Yeah, because I sent the message and it didn't show up, and I kind of waited 20 minutes and it still hadn't showed up,
Really?
and so I was like, okay, I'm going to send another one.
It's like a half an hour almost.
Wow.
Yeah, and so and I noticed some other people after I was registered kind of had the same thing, and so I wondered if it was because it was moderated, and so we should just kind of be patient and eventually get it through the queue, or if it was just been running slow or something.
I've never witnessed that long of a delay before. I mean, like a minute, but not.
Yeah, I did it, and then I went and did some other stuff, and I came back and checked, and it still wasn't there, and it was at least 10 or 15 minutes. So, and when you did it, it was just instantaneous, which is why I was like, oh, well, he's the creator of the group, and so it's like, he just gets to send stuff, and so I was like, well, maybe it's moderated.
Did you email it or did you post it
Through the web one.
I've never seen that kind of a problem.
Okay.
Hopefully that doesn't continue.
Okay. So we just need to be patient when we send it.
Yeah.
Okay.
Although I have had emails before from students who've, like a half hour later, if I haven't answered the question, they're wondering why I haven't answered the question.
That's another issue entirely.
Okay, real briefly, I want to, if you haven't looked at it already, this is what the video from our last class looks like. I'm not going to plug it in, so we won't have audio. Eventually it will come up. There's the video. So just push play. And you can relive the experience from our previous class. What you'll notice here is, you can go full screen in the bottom right-hand corner. If you see where my mouse is, in the bottom right-hand corner, you can go full screen if you want to. Also, a really cool feature of this. Oops. Sometimes I have problems with this. I don't know why. Well, eventually it will go totally full screen if you don't mess around with it. So once you hit your mouse, or if you click in it, then this little thing up here comes up. And let me get out of full screen so I can show you this aspect. So you can actually search the audio. So that's really cool. So if I want to look up the word Bootstrap, when did I say Bootstrap? I bet I said it a few times. And here will pop up, it converted my audio to text. It's not a perfect conversion. Second semester I've used this. It's not a perfect conversion, but this can be helpful to find certain portions of the lecture when I said a particular word, if you want to go back. So it's a nice little interesting feature of that. Also, one other thing here is that, so you see me in the lower right-hand corner here. Let's see if we can come to a point where this looks.
Nice pose.
Anyway, maybe there's a good point. There we go. So you can see it's a little bit transparent, that video there, of the live action video of me. I personally don't like that, and I talked to some of the administrators of this Cam Relay package on our campus, and they said it cannot be changed. So sorry, that it will be a little transparent there. I guess it's not a big deal, but it just kind of makes me look weird. So that exists there. And I think I mentioned this last time too. This is they've upgraded their package from last semester. This is the first time that they've been able to include the live action video there. And so I started recording my lectures about 6 years ago, and using some other software to do this stuff, my own software. And finally, after 6 years, the university has the kind of system that I want to use for my class captures. They're pretty close, other than that aspect there, the transparency. And also, I usually like to have like a table of contents over here, but I can't do that. Anyway, it's a nice tool. Any questions? Okay. Let's see. Oh yes, and there's one other thing I wanted to talk about. So when you download my lecture notes, so let me just download some lecture notes here on my desktop. And when you open up my lecture notes, you're going to have the lecture notes look like this. And there's a few comments I want to make. First of all, notice we have this highlighted area here. This is just a comment that I put in my own lecture notes. And by default, the way that Word will display the comment is it displays in what's called balloons. I at least find that annoying, especially if you were to print this off. The balloons would be printed as well. So if you want to turn that off, you can go under Review, Show Markup, Balloons, Show Revisions, all in line, and then they disappear so that when you print your notes, they'll look a little bit better. So just one little comment there. And I guess these comments that I put in here, these are just reminders to myself. I mean, you're welcome to read them, but generally speaking, there's not stuff that you need to know. So this in case, here, for example, is a reminder for me about something. Second, now I don't think I mentioned this last time, but the font size that I'm using here in my notes is a size 20 font, as you can see. And the reason why I do that is that these lecture notes appear well on any kind of data projector in any kind of room that I teach in. But you know what this means then is if you were to print off these lecture notes one page at a time, they're not going to look very good because you have this very, very large font. So if you want to print it off like 4 per page, like similar to what I did here, if you're not familiar with how to do that, go to File, Print, come down here, 1 page per sheet is the default, and you can simply do 4 pages per sheet instead. Some people prefer 2, I prefer 4, and that will allow you to print them off a little bit nicer. And lastly, in order to do my equations, notice how my equations here are in gray. I purposely have these highlighted to help remind me that these are equations. These are created through using a software package called MathType that some of you are probably familiar with. So I'm not trying to highlight these equations. It allows me to see where the equations are more easily when I update my notes. But if you're not familiar with MathType, if you don't have MathType on your computer, some of these equations, when you download my Word lectures, these equations might not look right. And the reason being is because you don't have MathType's special fonts installed on your computer. To get then these equations to look correct, you can go to the MathType webpage. I have some information here about how you can download their fonts. Any questions?
Is it the screen or the projector that's creating that like wavy thing that keeps going up and down?
I haven't seen the wavy thing yet.
Okay, you pick the Word document.
Okay.
You can see it more easily. You look in the light.
Oh yeah.
That's totally projector.
Okay.
Yeah. It's tough to get rooms on campus. And it's tough to get rooms that are nice rooms. This is a fairly nice room. Ooh, that's still there. We'll have to deal with it today, but I agree with you that I would find that annoying. I will contact our computer support person. Hopefully we will get some help. I at least don't remember it being like that. I taught in here last spring. I don't remember seeing it. Does it happen with other?
It's just harder to see when there's like a white background.
Yeah.
It's still there. It's just not quite as obvious when you have the gray versus the white.
Any idea if I could change the change the gray background? It's all white. I mean, that's the best I could probably do. It's still there, just not maybe as noticeable.
That feels better.
Well, as an alternative, what you could do is actually look at the lecture notes on your computer screen. But yeah, I will contact a computer support person, but I cannot guarantee that a solution will be found. Yeah, another problem with this room is that you got this kind of loud air thing up there. Not a good thing for my microphone that I'm using to record this, because you can hear it in the background as well. And last semester, or when I was teaching in here, due to where the sun was in the sky, it was this time of the day, the sun would come in here and have a big glare on part of the screen. I don't know why we have to go through these things when we teach. Okay. Any other questions?
To keep us on our toes.
So if you all have headaches after looking at that screen there, you can blame me. Okay. So let's review a little bit where we were. We left off on page 9, but I want to review one thing that's on page 6. So I think this is very important, because we're basically going to do something very similar to it shortly. So, we talked about it's very important to be able to come up with the sampling distribution of your statistic of interest T. Once you get that sampling distribution done, then you can do statistical inference. We looked at 3 different ways that we can approximate that sampling distribution. One way would be to assume that the distribution of F was actually known. Remember what the distribution of F represents. Let's say that Y1 through Yn are distributed F. So maybe normal, maybe gamma, maybe something else. Or maybe it's just some distribution you don't exactly know. But if we didn't know it, then we can, generally speaking, let's say, analytically derive then the distribution of T, which we call G. If, though, we didn't want to actually go through all those math details, what could we do then to maybe approximate then this distribution of T? Well, we could use Monte Carlo simulation. And what we said was that you could take, let's say, R samples of size n from this distribution of F. So, for example, you could say you get, let me pull my red pen here, so let's do blue. You could get Y11, Y12, down to Y1n. So for the first sample from F, that's what the first index in the subscript means, you can get Y1, Y2, down to Yn. Then for sample number 2, you can also get Y21, Y22, down to Y2n. And we can keep on doing this until we get to the rth sample. Okay? Once we have that information, then, we can compute our statistic of interest on each of these samples. So I can compute, let's say, T1, T2, down to T sub R, capital R. And then we can get an estimate of what G is. You can graph it with a histogram. You could use an EDF to see an estimate of the CDF for G. You could do a variety of other ways to summarize that probability distribution. So, for example, once I have this estimate of G, I could, for example, estimate then the probability that my random variable T is less than a particular observed value of T by simply taking the number of these T sub R's that are less than or equal to a particular value T.
What does that say right next to after the parentheses?
Using. Sorry. So estimate that probability using G hat. Sorry about that. Okay. Now, in real life, again, you're not going to know what F is. And so we spent some time last time talking about, well, maybe we could just replace F with an estimate F hat and basically do exactly the same thing. And we talked about, well, how could you get F hat? If you want to go completely non-parametric, what you could do is get this EDF, the empirical distribution function, which is an estimate of the CDF. And we looked at, for example, a graph of the EDF. It looked like this for a particular sample size of 20. I think these were GPAs. And this is my estimate of F. Okay. So if I still want to estimate G then, what I could do is, again, take R samples of size n from this F hat. For each sample, calculate TR, and then summarize. And there's your estimate of G. Well, how do we take samples from F hat? And that's where we left off on page 9. It's actually really, really, really simple. What we can do is, for your first sample from F hat, sample from the Y1, Y2 down to Yn with replacement. So maybe you might get Y1, Y2 down to Yn all again, or maybe you might get 2 Y1s, not a Y2, but then Y3 through Yn again, once. Now, since we are sampling from our, let's say, original sample, go back to my document here, typically, and this is what we will do, people will now put stars on these sampled values from F hat to differentiate Y1 from Y1 star, say. So Y1 star would be, let's say, your first sampled value from F hat. Y1 is your first sampled value from F. So we sample with replacement. A sample size of n. Since we are sampling from our sample, this is called resampling. So here's the first resample, here's the second resample, and here's the capital R resample. Why do you think we sample with replacement instead of without?
Just gonna get the same thing.
You're going to get the same thing over and over again. Well, that's no fun.
Oh, look, we got all this.
Yeah. But there's actually another more mathematical way or statistical way of thinking about why do we resample with replacement?
To not modify the original distribution?
Excuse me?
To not modify the original distribution?
To modify the original?
To not modify.
I'm sorry, I'm not for sure what that first word you said.
Because if we sample with replacement, the distribution will be not the same for the second resampling.
Well, I mean, are you saying if we sample without replacement, obviously you get the same thing? Okay. But I'm looking for something else.
To ensure that you can.
I'm sorry, what?
Like, we assume an infinite sample, or not, we assume an infinite population size, and so, versus like survey sampling where you have to find, I don't know.
I think you're kind of getting at that in terms of what's the probability of getting a particular item sample. Now, you know, in before this class, in the non-Bootstrap world, what you would have done to take a simple random sample is that every single element in that population has an equal probability of being chosen. And if you have an infinite population size, if you assumed infinite population size, that's, you know, fairly easy. You know, if you have a finite population size, obviously that's a little bit more difficult, but it could be done. You know, think of, you know, we were talking about that GPA example. You know, we have 25,000 students here. Well, you know, the first student that you pick out has a probability of being chosen 1 over 25,000. Well, then the second student's 1 over 24,999. Well, would we actually, in actual application, make some changes to our analysis because of that, or would we assume it's a simple random sample? Assume it's a simple random sample. So, if I want to duplicate the fact that I'm taking a simple random sample from my population of interest, what I want to do is basically sample from Y1, Y2, down to Yn, such that each of these has a probability of being chosen of 1 over n. That's why we sample without. I'm sorry. That's why we sample with replacement.
It's like Y1 is representing all of the items in the population that also would have the same value that Y1 had. Sort of. Kind of.
Maybe. I mean,
and so you could conceivably, if you were going to the population, take another sample, you could get, you got Y1, and so then you sampled again, and that one also had the same value as Y1. And so the fact that in resampling you may get Y1 twice, it's this kind of. Okay.
Sorry.
No, that's fine.
That's my official response. There is actually something similar to what you're saying, though. And you'll see that in Chapter 3. There's a short section on survey sampling where you're using that same kind of logic. So stay tuned for that.
Okay.
So anyway, so we want to do a simple random sample. Every element in your population typically has equal probability of being chosen. So we have to reflect that then when we take our read sample. So that's why every element has a probability of being chosen of 1 over n. Okay. So once we have, let's say, capital R resamples, what we're going to do is calculate our statistic of interest on each of the resamples. And so instead of calling it T1, T2 down to TR, let's actually put stars on the T's to reflect the fact that these are coming from resamples. Then, if we summarize then all these T stars using a histogram or using other means, we have an estimate of G, the sampling distribution of T. This is what's called the non-parametric bootstrap. And again, this all works out because remember F hat is a good estimate of F. And it all comes down to what I was originally saying yesterday when I first wrote this up, that if we didn't want to know if we didn't want to do the mathematical calculations and we had F, we used Monte Carlo simulation to actually come up with the distribution for G, or for T, which is G. Any questions? So that's the bootstrap. So page 10. Let's talk about an actual numerical example. So let's suppose that we do have 20 UNL students in a sample. They were randomly selected from the population of all UNL students, and their college GPAs were obtained, and I didn't actually do this. I actually simulated from a normal distribution for mean 2.505 and variance of 20.25. So let's look at how we actually implement some of this stuff in R. Make this a little bit bigger. There we go. Okay. Let's see. So the first thing is I have the data. I'm sorry. Excuse me. I'm going to simulate the data from using a normal distribution. So use the R-norm function. I'm going to set a seed, of course, so that I can replicate my results at a later time. And we make this a little bigger as well. Okay. So there's the minimum, there's the maximum. Sorry, there's the wrong thing. And so what I could do is just simply print off my sample so that you can see it. Again, my statistic of interest, the actual observed value, I'm going to call that T, and its statistic of interest is 2.56. Now, the first thing that we want to do is take a look at an EDF. So we've already looked at this EDF before, but we haven't looked at how to actually do this in R. And I expect this part right here will be new to most of you. There is a function R called plot.ECDF. R just happens to call it the empirical cumulative distribution function versus just empirical distribution function. And if I were to, let's say just simply, for the first argument, say x is equal to y, where y has my data in it, and plot that, you can see that I get a plot that looks like this, which looks a lot different from the EDF that I had shown before. So what this means is that we have to, in order to get it to look like an actual EDF that typically most people actually represent, we need to use some of the arguments inside of the plot.ECDF function to do this. First of all, notice how we have no vertical lines here, as we would typically expect. So what we can do is say instead, verticals equal true. The do.p argument, that's what gives you these points here. That corresponds to where we have values of actual y values. Well, we don't need points there, so when we say do.p is equal to false. Then I put, of course, these are common arguments. Put a nice little title on my plot, line width of 2, so twice the normal. I'm going to put some grid lines on it. For my y-axis, I'm going to use the expression function to allow me to put a hat on top of f, and then, of course, a label on y. So when I execute this code, and there's my nice little EDF plot, like we had seen before. So what I like to do is now take a sample from basically this distribution, and in other words, do a resample. So to, again, duplicate what so that I can duplicate my results later on, I'm going to set a seed, and then I'm going to use the sample function R to take my resample. Sample, first argument is x. I'm sampling from y, which is a vector, again, that has my data, and then with replacement. So replacing true. And then I'm going to put that into something called y.star, for the lack of a better name. When I find then the mean of y.star, I put that into t.star, and I simply print off the results with the cap function. And this is what we get. So there's my first resample. Note that I did sort here. So notice 1.537, 1.537, my original sample. You notice here I have 3 2.426s in my resample. And my T star is 2.5891. So that would be my sample mean from the resample. And I could use the table function. You've seen this function before. This just allows me basically to come up with a frequency distribution. So table of y is my original sample. Of course, each element's represented once. Then table of y dot star, we see those three 2.426s. We also have some other duplicates here as well. Okay, so page 13 then. That's great that I can do one resample, but of course we need to do more resamples to be able to estimate this distribution of G using the Bootstrap. So how about I take 1,000 resamples. We'll talk about later in the semester why I chose 1,000 versus maybe 5,000 versus maybe just 100. We'll just do 1,000 here. Set a seed against it, I can reproduce my results. And basically what I'm going to do is I'm going to create a matrix. Inside this matrix, every row is going to be a resample. So row 1 is going to be the first resample, row 2 is going to be the second resample, and so on. So we're going to initialize a matrix with NAs. In other words, we just need to put something in there first. Capital R rows, N columns. And there's a few different ways in that we can take these 1,000 resamples. I just simply chose a for loop to do that. So I use a common for loop where, notice I use the same code as we saw before. I use the sample function to do my resampling. And then I always put the results from every iteration into row I corresponding to the for loop. Anybody like me to go into any more details about this for loop? Okay. So let's do it. Okay. It takes no time at all. If I use the head function with my save.resample, we can see the first 6 resamples given there. Of course, if you've ever heard of the tail function as well, that allows me to look at the last 6 by default of, in this case, my resamples.
What is the more efficient way to do it than before?
Well, you could simply just take all the resamples at the exact same time versus having to do one resample, do another resample, do another resample. You can think of it this way. Let's say that I want to sample from a normal distribution. Let's say I want to take 1,000 samples of size 10 from a normal distribution. You could put R norm in a for loop, or you could just simply say, why don't we take a sample of 10,000 from the R norm all at once. And also the fact, too, that there's actually going to be a function R called boot that allows us to do more efficiently as well. Okay. So let's actually look at now a summary of all these resamples that I got. So what I'm going to do is use the table function. Remember we did that to come up with a frequency, basically the frequency for every element, for every unique value of y's that we were getting. So I'm going to use the table function to help me summarize how many times did I get a 1.537? How many times did I get a 1.804? And so on. And if I were to divide that by capital R, we can see proportions. And you would, or I'm sorry, not proportions, but the expected number of times that you would expect each of these data values to be in a resample. So notice how each of these are about 1, which is what you would expect if 1.537 has a probability of 1 over 20, 1.804 has a probability of 1 over 20, and so on. So I got these resamples, and what I would like to be able to do is basically what I demonstrated on this Windows Journal thing that I wrote up here. I want to calculate T1 star, T2 star down to T sub R star. In other words, I need now every row of my matrix, I need to find the mean. The quickest way to do that probably would be to use what's called a row means function. But I'm going to use the apply function instead because it's more generally applicable in those situations. Does anyone know what the apply function does?
This is apply this function to whatever you tell it to.
Yeah, apply a particular function to every row or maybe every column of a particular matrix of data. In this case, save.resample contains my resamples, 1,000 rows of resamples. I want to apply to margin equal 1. It's just what they use for row. The margin equal 2, that would mean column. And then lastly, what do I want to apply to every row? The mean function. So I apply that. I put the results into t.star. So that t.star itself is now 1,000 different sample means. I could do a summary of t.star, find the standard deviation of t.star as well. So you can see that on average, I get 2.56. The standard deviation, just a regular old sample standard deviation that you would typically calculate on a group, on some data, is 0.0914. Okay. So this is trying to estimate, again, the standard deviation of t. Now we actually know another way to calculate that standard deviation, or to estimate that standard deviation. What we could do is take this s squared, s, let's say your normal sample standard deviation, how you normally would denote it, s divided by the square root of n, right? Learn that in your very first stat course. This is what I get, 0.0958. So, this is the Bootstrap estimate. This is what you would have done before you got to this class. Notice how close they are. Now, in order to get this estimate, you needed to know some math. You needed to derive some stuff. With this estimate, all you need is basically some computing power. But what is the true standard deviation? Well, I simulated the data, so I know it. I know what sigma is. So sigma divided by a square root of n is 0.11. So they're both underestimated. But still, these estimates are going to give you about the same thing. Okay, well let's think about a bigger problem here. Well, let's say that you have a particular research problem, and you have a statistic. And one of the first things that you will want to do is calculate the variance of that statistic, because that's useful for like confidence intervals and hypothesis tests. So what you're going to need to do is maybe use some math to derive that variance of that statistic, or standard deviation of that statistic. Alternatively, use the Bootstrap. That's it. That's all you need to do. Now, when would this actually be done in research? Well, if you have a complicated statistic where the actual mathematical derivations are difficult, then use the Bootstrap. If the calculations are easy, such as in this particular problem, well, we'll just use s divided by square root of n. Okay, let's look at something else. How about we look at the EDF of the T stars? So that's what the EDF looks like. For comparison purposes, then, let's also plot. Oh, let me ask you this without you looking at my notes. What would we want to compare this too. In terms of what would you have done before this class, what would have been an estimate of G? We have a sample means or statistic. So what would you have used? Mean what?
X bar. Standard deviation.
So Y bar, let's say.
Right. Yeah, sorry.
That's fine. And then a variance is S squared divided by N. Sample variance divided by N. That's what you would have done before if you needed to estimate this distribution. Well, let's look at a plot of that. So I have the curve function here that allows me to simply plot now a CDF of a normal with a mean of Y bar and a variance of S squared divided by N. And this is what I get in blue. Not much difference. And again, let's think about where this normal distribution comes from. Well, it's not until you actually take a course like Stat 980 do you really see the derivation of the central limit theorem and actually go through all those details. Some high-level math there. But with the Bootstrap, just take some resamples and you got it. Now again, in a research situation, what you're going to often be faced with is that you're going to need to figure out what's the probability distribution of a particular statistic that you have. You could do some math and derive it, but maybe if the math has become a kind of complicated and stuff, or it just isn't working out, use the Bootstrap. What's the actual distribution, though, in this particular case? Well, I know what mu is. I know what sigma squared is because I set it when I simulated data, so I can use the curve function again and plot then the true distribution. Let me actually put a legend here too. And the true distribution's in red. Okay, so yeah, we're not perfect. But again, we have a sample size 20. And, maybe that wasn't enough to get that good of an estimate, but it's not that bad. Would anybody like me to talk about this curve function here? How this curve function works? Yeah. Okay. So this curve function is a very useful function R that I use to plot those distributions up there. And an easy way to see how this curve function works is that, well, basically I should say, it allows you to plot functions of one variable, where the function that you put is in the expr argument. And if I say curve expr equal, let's say that I want to plot f of x equal to x squared. Okay. So I put an x squared in there. And I want to do it over the range -3 to +3. So I use the excellent argument to do that. And there's my f of x equal to x squared. Really simple. And basically what it does, by default, it picks 101 values between -3 and 3 and evaluates the function and then just simply plots it. You can change the default of 101 to something else if you really wanted to. In a little more complicated situation, suppose I want to plot the standard normal. I could use the dnorm function to give me my f of x for a standard normal. And I can say dnorm x equal x, mean equals 0, SD equal 1, standard deviation of 1. And there's my standard normal distribution. The key thing when you're using this curve function, you always need to make it a function of x. So you always have to have an x on this somewhere over here. So notice how I put it here, and also I put it here. So let's say if you had defined your variable to be y, and f of y had a normal distribution, well, you couldn't put y there, you need to put x. Any other questions? Very nice function. Well, also for comparison purposes, and just to show you some functions that we're going to be using, we can compare quantiles of these distributions in terms of the actual normal distribution or this, this distribution that we're estimating through the Bootstrap. So there's a function in R called quantile that allows you to compute quantiles. We'll use this function a lot. And I'm going to find quantiles of t dot star. And remember, I have 1,000 values in t dot star. So you would think that I can get maybe some good estimates of my quantiles of the distribution. The probs argument allows me to specify which quantiles I want. Now I'm going to take a sequence of numbers from 0.05 to 0.95 by 0.05. So if I put that all in an object called t.star.quantiles, those are my 0.05 to 0.95 quantiles from the t-star distribution. We can then find exactly the same kinds of quantiles then from this normal distribution that we would have normally used before this class, where we have, again, a mean of t, a standard deviation of what would be s divided by square root of n. So I can use the q norm function to find those quantiles. Put this all in a data.frame so we can compare. And we can see, as you would expect, that these quantiles are very similar to one another. Notice how we see a little bit of deviation right here for the 0.95 quantile. Well, let's compare that to our plot earlier. That corresponds to this area up here. Notice how that's where you see the little bit of deviation. And lastly, what we could also do is do a little histogram. So I can use the hist function to find the histogram. Note that I'm going to use an argument here that you may not have seen before with hist, and that is freq equal false. If we don't have that, first of all, I'll show you what happens. Let's try that again.
It's because you have the y limits in your histogram.
Oh. I just put that there to control the scale. So this is what our histogram looks like. Notice how it's symmetric, as we would expect, since we know that this normal distribution seems to be be very similar to this distribution that we get from the Bootstrap. On the y-axis, notice we have frequency there, as you would expect for a histogram. If instead, though, we put freq equal false there, as you might expect, it's not going to be frequencies there. Instead, what will happen is that the plot will look exactly the same, but now the y-axis is going to be scaled in a certain way so that you can plot a probability distribution on it. So that's why you see density there. If you want to know how that rescaling is done, you can talk to me after class. And so let's plot then this, I think this is something that was left out of the notes. Yes. This right here, I'm going to plot this first. This is the actual distribution that we would have done before this class in terms of a mean of y bar, standard deviation of s divided by square root of n, and as you would expect, we have a very similar shape. If we plot then the true distribution, since we simulated the data, this is what we get. And you can see that little deviation. The key thing is that the Bootstrap will produce very similar results to what you would have got through using conventional means, let's say, before taking this class. Okay, so page 17 then. Are there any questions first? So, we see that the Bootstrap estimate's very similar to this normal distribution with mean. And the y, I have an x bar there, so sorry about that. That should be a y bar. Variance s squared divided by n. So the two are very similar. Why would one want to use the Bootstrap here? Well, you wouldn't. Well, yeah, practice. Yeah, this is academics. We do stuff like this. No, you wouldn't want to use the Bootstrap. But the reason why I did this is because it's a simple example and allows you to see similarity between stuff that you've done in the past to stuff that we're going to do now in this semester. it's nice when those kinds of things match up. Okay. Let's move on then. Let's talk about a quick history of the Bootstrap. The Bootstrap is now about 35 years old or so, 30 years old. And the person who generally gets credit for it is someone by the name of Bradley Efron. He's probably one of the most famous statisticians out there. He's a professor at Stanford, one of the probably top 3 Department of Statistics there. I think most people would agree on. And other people had come up with portions of the idea, but he kind of put it all together. The early work comes in the late 1970s, where this idea was first proposed. And imagine what computing power was like back then. Imagine what people would have said or thought when someone's proposing, I want to take these resamples 1,000 times to do this kind of stuff. People would probably, I was in grade school, and probably a lot of you weren't even, most of you, all of you probably weren't born yet. I was really young, to say that. So I don't know what people were saying back then, but I could just imagine probably what the thoughts were when this first came out. It's like, you're never going to be able to actually do this. But this is actually, I think, a good example of one of the beautiful things about research, that somebody has to come up with the idea first. And just because you can't do it now does not mean it's not going to be important later on. Efron, I think almost always goes to the Joint Statistical Meetings, JSM. This is the biggest group of statisticians in the world that meet once per year. I think some of you were there as well in San Diego when we met a few weeks ago. About 6,000 statisticians were there. But Efron skipped JSM one time back in 2007 for a very important reason. He got an invitation from the president to get the National Medal of Science presented to him. So this is a big deal. This shows you how important the Bootstrap is to science itself, not just statistics, but to science. And this I got this from the ASA's American Statistical Association's website, and this is Efron was cited for his great achievements, including Bootstrap resampling technique. We don't normally put the hyphen in there. I guess I credit George Bush for putting the hyphen in there. So sometimes we won't go into those details. So obviously that's a real big thing. And if you ever go to a joint statistical meeting, I encourage you to search to see when Efron's presenting, because he's a very good presenter. I, in fact, went to he gave a presentation on some stuff with the Bootstrap this year, and he did a good job. In fact, we may, depending upon what we do, may actually use one of his data sets that he was talking about in that presentation. Okay, so where did this name, the Bootstrap, come from? It's one of the few interesting names out there in statistics, and it actually came about as a reference to a book called The Adventures of Baron Munchausen. Anybody heard of that book before? Neither had I before I took a course on the Bootstrap. But there was a 1989 movie on it, so if you really want to do some homework, go watch the movie. It's actually not that good of a movie, I must admit. But anyway, it's a very old book, and so it's old enough that the copyright, I guess you could say, has expired on it, and you can actually look at it on the web. And the Baron was noted for in his book, the book about the Baron. The Baron often did some quite extraordinary things that you can't really do it. And one of the things that happened in this book was that the Baron was stuck on the bottom of the lake. Just standing in the lake, looking up, you could see where the top of the water was. Well, obviously, he needed a way to get out of the lake. So what he decided to do was pull himself up by his bootstraps and get himself out of the lake. You know, if you're pulling yourself up, you're pulling your leg up, so that means that you're actually pulling your whole body up. Obviously, that doesn't make sense. But that's how he got out of the lake in his book, John Tukey, probably all of you have heard of John Tukey, one of the most famous statisticians as well that has ever been around, thought that the idea of using a sample to generate more data, which is basically what we were doing with resampling, was like the trick by the Baron. You shouldn't be able to. Why would you take a sample from a sample? You already have the sample. And so he thought this whole idea behind this was kind of like what the Baron did. And so that's why he suggested the name, the Bootstrap. And in fact, there were many skeptics at first when this first came about. In fact, I still remember attending a Department of Statistics seminar when I was a grad student at Kansas State in the mid-1990s. One of our professors, actually, who will be my advisor, was given a presentation on the introduction to the Bootstrap. There were many faculty in the room from our department, and a lot of the really important faculty were there, and they were like, yeah, okay, sure. Yeah. They weren't, well, maybe they weren't doing it that much, but they were skeptical. You could tell that they were skeptical. So even in the mid-1990s, people were still somewhat skeptical about this idea. Now, here's an actual excerpt from Efron's paper that really put the Bootstrap on the map. This is the acknowledgement section. And so, this is where you say thank you, thank you, thank you, thank you, thank you for doing this, and so on. And towards the end, I want to focus here. He says, I also wish to thank the many friends who suggested names more colorful than the Bootstrap, including Swiss Army Knife, Meat Axe, Swan Dive, the Jackrabbit, and my personal favorite, the Shotgun, which, to paraphrase Tukey, can blow the head off any problem if the statistician can stand the resulting mess. Quite an interesting quote. Tukey's named a few things out there. Anyway, I don't see that much in the statistical literature anymore, unfortunately. So what's the current state of research in the area? Well, most of the stuff's been figured out. 1980s and into the 1990s, the theory behind the core principles of the Bootstrap were figured out. Okay? So if you want to do research on the Bootstrap itself, stuff's been figured out. Okay? But the Bootstrap, and there's still some small research that's done. It's very, very mathematical. Typically, like in a journal like the Annals of Statistics, if you're familiar with that, that's where the research would appear. But there's not a whole lot of stuff done on core Bootstrap principles and ideas. Instead, though, the Bootstrap is used a lot. Notice I use the word used. It's used a lot to solve research problems, such as I've been telling you in terms of you created a statistic and you need to know what is that statistic's distribution. Just Bootstrap. So you'll see this used a lot in the statistical literature and even in the non-statistical literature. So what are we going to do then in this course? Well, I kind of addressed this a little bit already, but it's good to talk about it a little bit more. Like I said, what we're going to do is talk about the core principles of the Bootstrap, and we're going to focus on applying the Bootstrap to solve, you could say, relatively simple problems. The reason why I have to do that is because, the Bootstrap's used in many, many, many different areas of statistics. And in order to fully understand what the Bootstrap is doing, you need to understand like survival analysis, spatial analysis, time series, or whatever statistical area of interest. And we can't put those as prerequisites for one course. So that's why we stay with, I try to stay with, problems that I'm sure that all of you are familiar with in terms of the applications of the Bootstrap. What this means is that there are obviously the areas of the book that I can't do. In particular, there's a number of areas in Chapter 3 that I'm not going to be able to cover. So, for example, there's a section there on survival analysis. A section on survey sampling, which I'll talk about just very briefly, but unless you've had our Stat 804 course, I think it is, it will be tough for me to go over it in detail. So, we'll do Chapters 2 through 6. A lot of the material in those chapters. 6 goes up to linear regression. We might talk a little bit about 7, which talks about generalized linear models. We won't do, pretty much won't do anything out of 8, 9, or 10. There's a short section in 9 that I think I'm going to add this year that I haven't talked about before in the past. It talks about how to make the computation in terms of taking the resamples faster. Now, obviously, what you saw here is that resampling was pretty fast. But let's say you have a complicated statistic that might take a minute, 2 minutes, 3 minutes to calculate on a computer, or even longer. Do you really want to take 1,000 resamples? Well, it might take a while. There's things that you can do to speed up the processing time. Chapter 11, please remember that is an important chapter. We won't do it directly, but this will help you with the R stuff. Speaking of R. Well, first of all, are there any questions? Speaking of R, the rest of this Chapter 1 stuff is going to talk about R and specific parts of R that some of you may be familiar with, some of you maybe are not familiar with, that it's important for all of you to be familiar with. So some of this will be reviewed for some of you, others it may not be a review. If, I don't think you'll need this, but if you did, you can, if you want to see how I introduce R in a classroom situation where the prerequisite is no R at all, take a look at my Stat 875 course website. I have some notes there on that. So, all of you should know that R is broken up into packages. Basically what a package is just a collection of functions. Maybe also some data in there as well. There are over 3,000 packages. I won't be surprised if it's up to 4,000 by now. And what makes R, what's made R so popular is the fact that anybody can write a package. You upload it to the R website. It's called the Comprehensive R Archive Network, or CRAN for short, and then others can download it. This is the most common way that people now disseminate their research to others. Write a paper, let's say in Jazza, get some R functions that actually implement your method, and people can now download it through CRAN. It's very, very commonly done now. And it's really made it easier to implement research, new research, the most current research out there. So, a number of times during the semester, we're going to need to download some of these packages. Simply install them from the packages, install packages. Up will pop up a whole bunch of mere websites, or servers, I should say, across the world. And if I go to Iowa State's website, and up will pop up all these packages here. So there's a number of packages, for example. We talked about the boot package. This is already installed in R, so you don't need to actually reinstall it. But you can see there's a number of other boot packages here as well from other people have written. This Bootstrap package is actually what corresponds to S+ functions that were written for the Efron and Tim Sharani book. So there's one, and another one. It might be helpful at least at the beginning of the semester. Here we go. There we go. Simple Boot, which allows you to do simple Bootstrap stuff. If you want to know about various packages out there that involve the bootstrapping stuff, how could you figure out what packages are out there that involve the bootstrap? without seeing like the name Boot. Any ideas? Well, let's go to my website, link to stat resources. Packages written by users. Here, it's sorted by name. Oh, there's 4,001. Look at that. 4,001 available packages. Packages sorted by name. What you can do, this is what I've done in the past. Let me just do a quick search. Let's do a search for Boot. And you can see all the various packages that involve something dealing with the Bootstrap. Okay? So that might be helpful. Now, with each of these packages, what you're going to see is that there is actually a corresponding web page to them. So let me go back up to Boot itself. So we a good demonstration. Sometimes if you, all of you probably have installed packages and stuff, but maybe you haven't paid as much attention to it as you maybe should have. And if you click on Boot here, what you're going to find here is a description of the package itself. And you will always find a reference manual. This is just a simple PDF that contains information on all the functions that are in it. Quite frequently, you will also find another thing here for downloading called vignette. And what that is the authors of the package have put together like a little help manual about how to use the particular package. And that could be very useful at times to figure out what the package is doing. What about R help? Well, there's a variety of different sources for R help. And again, the way that I usually get R help is I go under help, HTML help, and that will open up this little web page here. Here's a whole bunch of manuals, PDFs that give you some help on R. Using R, I usually go under packages here, and I find the boot package. And for example, if I want to find information about the boot function within the boot package, here is a help file on that. So we'll be using this boot function a lot during the semester. But there are other sources for help that I wouldn't be surprised most of you have not encountered. First of all, if you're struggling with trying to figure out some R code, it's just not working. The first thing that I always do, if I can find it in the help that I just showed you, is to go to the R listserv. This is a very active listserv where you'll have over 100 posts per day, and you'll have experts on R responding to people's questions that are posted to the listserv. So, for example, let me go to this web address here. So this is in my notes. Here's the listserv's web page. You can subscribe to the listserv if you want. I don't anymore. I just decided not to anymore. What I use it more for is the searchable archives. So I go to the archives, and we have this nice little way that we can search for key terms, because if you have a problem, probably somebody else has already encountered the problem, so we'll do a search to see if somebody's posted a message before I had to answer. Simply what I will do is go here to search for my name, and you can see, for example, once when I had posted a question, this was back when I first taught the Bootstrap in 2006, and I couldn't figure out something, so I posted a question here. Here's my question, and you'll notice here down below, Brian Ripley replied to it. He's part of what's called the R group. It's about 20 people or so that are the ones that actually control the main part of what R is. So I had one of the experts come and answer my question, which was very nice. Now, the traffic on the R listserv for the first time over the past year is starting to decrease. Before it kept on going up and up and up and up. And one of the main reasons is because there's this fairly new website that first came out a few years ago called Stack Overflow. Anybody use Stack Overflow before? Well, good. Stack Overflow is a website for not just R, but for other software or other things. And what this is it provides a little bit more convenient way to ask a question and have people respond to it. And so what we have here, when I just go to the R version of Stack Overflow, the link that I gave you, what we see here are some people have posted some. These are the ones that are first coming up for some reason. Make this the most active currently. So some people are talking about how to make a great R reproducible example. It's a quick reading very large tables as data frames. So people have posted these questions here. And if we just go in here, we have then eventually responses. And they're usually sorted by what people have voted on as being the most useful to answer a particular question. And so this provides a very convenient place where, here's a question, here are the answers to it, versus having to search the archives. This question was done on July 20th, 2006. Well, that's maybe not as convenient. And so this, I have started using this a lot more. I found this to be quite helpful. And again, you can do a search here. So if I do Bootstrap, up will pop up some problems that people have had with Bootstrap. In fact, actually, I didn't include R. And so R and the Bootstrap here. So I found it very useful. Another useful thing that I have found, and I recommend subscribing to if you find out that you really like R, and that is this Revolutions blog. This is put out by mainly David Smith, but also some other people who work for Revolution Analytics. This is a company, I think they're based in Seattle, or they might be in the San Francisco area, one of the two. This is a company that has a version of R that you can buy. Why would you want to buy R? It's free. Any ideas? Well, companies out there who want to use R, well, they could use the free version, yes. But what happens if something breaks down or they need extra help? It's so nice to be able to call up a company and say, can you help us? And so basically what they've done is they've created their own little graphical user interface and added some additional functions and also put R into it. A number of companies, at least from what I've seen through listening to this or watching this blog, a number of companies actually purchase R, you can say, through them at a much lower price than cents. So this is a very, very nice blog that teaches you stuff about R. And in fact, you can do a little search down here. So if you search for my name, guess what? He had a little blog entry about myself a few years ago about how you can use R to detect Cylons. You want to know more about that, read the blog post. Page 124. Here are a number of other resources as well. There's an R wiki out there, a way to search Google where things are filtered out, so R is only return items that come back. R by example, and I have found this to be interesting as well. The R language tip of the day. I have R language tip of the data. No, that should be day. Okay, let me fix that. And lastly, because I know we're out of time, I forgot to show you this. I don't know why I didn't when I was talking about the Baron. So that movie I was mentioning, about the Baron. They actually talk about the part where he supposedly is supposed to pull himself up by his bootstraps to get out of the lake. Instead, I guess they used a different translation. It's a German, it was original German, but they used a different translation. And in this particular translation, instead of pulling himself up by his bootstrap, he is on his horse and he pulls himself up by his ponytail. So, when I was watching this movie for the first time, I was like, oh, I can't wait until he pulls himself up by his bootstrap because I want to show my students that it's ponytail. Anyway, so I was kind of disappointed when I came across it. Are there any questions?
Is that Ian McCullough?
No. And this is from 1988.
That's true.
And then, I look at that and I think, that looks kind of like Patrick Stewart.
Yeah,
But it's
a bit
not.
like him too.
I don't know who it is, but it's not Patrick Stewart. But it would have been cool to have Patrick Stewart be in that movie. Okay, that's it for today.